Welcome back. So welcome to the third lecture of week 3 on probability theory with actuarial applications. Today we are going to move to continuous world and we will analyze some name distribution from continuous world. The distribution is exponential distribution. First of all, what is the need and why we are doing this, right? So we have the number of arrivals. So we modeled the frequency over a fixed time interval. Now the time interval that we are looking at can vary a bit. So we ask a question, what are the events that are expected in this time interval? That is where we come up with Poisson model, right, where it models the number of claims in fixed interval. Where for example, if I say lambda is equal to 3, whatever that unit interval is, I expect 3 events to happen. So if it is a claim, then I expect 3 claims per year and the interval is 1 year, right. So these are discrete random variables. Now imagine one claim has happened. Now I want to have an estimate of when the next claim will arrive. Okay. So this is where we are looking at time. We are not looking at the frequency of the claims in a fixed interval, but we are looking at how much time I need to wait for a claim to arrive. That is where our next model, which is the exponential model, shines. So this exponential model models the time until the next claim arrival or until the next event happens. So let us take this Poisson example where we discussed lambda is equal to 3 claims per year. So how much time will it take for the next claim to arrive? So we expect to wait until 1/3 of the year for the next claim to arrive, right. So this essentially means I am not dealing with discrete time points, I am dealing with continuous time points, and that is where this random variable that we will deal with is a continuous random variable, and it will take time values in the interval 0 to infinity, correct. So it is a non-negative valued random variable which is continuous in time. This is where the exponential model shines, and it is a very popular model for time to failure or time to claim or time for any event. Okay. So now we have understood why this model is required. Now let us understand the theory behind this model. What exactly is exponential distribution and why it is called exponential distribution? As we have seen clearly that lambda, which is the average rate per year or average rate of fixed time interval, plays a role, right. So this lambda we will take up and we will use that rate lambda, which will be in the Poisson process or the Poisson distribution that we discussed, and we define this random variable x following exponential lambda. Recall Poisson distribution, it was a discrete time variable which was actually counting the number of claims in a fixed time interval. Now we are varying time, okay, and time is a continuous random variable. So I will replace the PMF of Poisson with PDF of exponential. So the PDF of exponential, which is somewhat similar to Poisson random variable but very different from Poisson random variable, fx is equal to lambda e raised to minus lambda x for x greater than 0 and it is 0 otherwise. That is the complete description. Fx is equal to lambda e raised to minus lambda x for x greater than 0 and 0 otherwise is the complete description of this PDF. How does it look like graphically? It looks like this. On the right hand side the graph is displayed and you can see there is a towering value at point 0 and after that it decays exponentially, and that is why the name is exponential. The decay is exponential. At what rate this decay happens is characterized by the parameter lambda which is given here. right. So, I hope the name is clear. Because the rate of decay is exponential, the name of this distribution is exponential, and it depicts the exponential curve, right. Now, we have understood CDF, we have understood the setup and its connection with our Poisson distribution. Let us now consider a flip side of this, which is where the areas are counted. So, that will be our connecting point, which is the cumulative distribution function of this random variable. This becomes the main tool for our analysis, because this CDF has more convenient form than PDF. Let us look at the form of CDF and then comment on it. So, if I want to derive a CDF of this random variable, it is very simple. Fx is probability of capital X less than or equal to small x. So, I will simply replace this particular integral from 0 to x. Why? Because the random variable has non-negative density at x greater than or equal to 0. So, I will simply replace from 0 to x. This x, if you carefully watch, these are small x's, okay, these are not capital X's. So, these are small x's, and integral 0 to x ft dt, which will bring me to the density lambda e raised to minus lambda t dt, and then it is a regular integral, and you can see this fx, this again I insist it is a small x, not a capital X, and fx is 1 minus e raised to minus lambda x for x greater than or equal to 0, and it is 0 for x less than 0, right. It is a continuous distribution. So, whichever way I write less than or equal to, it does not matter, right. So, this is the complete description of my fx, okay. So, now since it is coming in 1 minus e raised to minus lambda x, there is one more function which we will define, because it is this random variable is characterized by time to failure or time to claim. There is another function that we will define, will be called a survival function, right. So, its survivor function is Sx, and this is complement of what CDF is. The event in the CDF, you take the complement of that and assign probability to it, you get the survivor function. So, this essentially means probability of x greater than x means, suppose x denotes the time required for claim, then it probability of x greater than or greater than x represents the probability that the claim has not arrived so far. That means the insurer has survived without giving any claims. So, this kind of interpretation, that is why it is called survivor function. Its probability of x greater than x, and you can easily see because of this structure, this is simply e raised to minus lambda x, which is the survival probability of the random variable x having passed time x. Now, we have understood the structure, the PDF, the CDF, and the new terminology, which is survivor function. Let us understand our key tools, which are mean and variance, summarizing the random variable. So, mean and variance, there is a common confusion among students. When we talk about Poisson, we say the rate is lambda, right. So, the students actually mix up with the roles of lambda and 1 by lambda. I will derive expectation and I will talk about it. So, if you look at this lambda e raised to minus lambda x, that function which is fx, and if you for x greater than 0, and if you integrate over x fx dx from 0 to infinity, that will simply give me expected value of x, okay. And now I will not do the integration, you can try it on your own. It's very easy because it's the exponential function that is being used. So you can try it. It will use some integration by parts formula at most, and then what you get is expected value of x to be equal to 1 by lambda, and this is what many people confuse. Expected value of x is 1 by lambda, not lambda, whereas in Poisson this expected value was lambda. Okay. So there is another form of this exponential random variable which is also very popular, where you actually treat this mean and then you write this as, so to avoid confusion I will write it as 1 upon beta e raised to minus x by beta, where x is greater than 0. And now if you look at this form, you will just see that this 1 by beta will be replaced with lambda. If I replace it with lambda, I get this. In these cases, the expected value of my x is equal to beta, okay, which is again 1 by lambda. So just ensure that in which form this exponential random variable is given, okay, and in this case the corresponding Poisson process will have a rate of 1 upon beta. So this is a major confusion for most of the students, so I am revealing that trap. You just look at the density that is given to you. If you are given a density in the form lambda e raised to minus lambda x for x greater than 0, then the expected value of this random variable will be 1 by lambda. However, if you are given density in this form, the expected value of this random variable is beta. Okay. So just make a quick note of this. You should never lose marks because of this representation. Okay. Let us focus only on one representation, lambda e raised to minus lambda x, and continue. Again using Lotus you can compute variance of x and it will turn out to be 1 by lambda square. If you have any questions in computation of variance, put in the forum, we will answer those questions, right. So we have clearly established the demarcations of exponential and Poisson random variable. Let us review them. First, when you talk about Poisson, if claims arrive at rate Poisson lambda equal to 3, that means 3 claims per year, then average waiting time, which is expected value of x, is 1 by lambda 1 by 3 of the year. Okay. So 1 by 3rd of the year you will wait for the next claim. Mean waiting time, that is expected value of x, is reciprocal of the arrival rate. Okay. So this should be very clear in your mind. Now let us look at some of the interesting properties of this exponential random variable, and this exponential random variable is a very useful random variable. It comes again and again in Poisson processes and in some queuing theory models, where this property that we will talk about is a memoryless property, is of great help for analyzing the models or simplifying the models. So whenever you are discussing exponential random variable, you are discussing a memoryless property. This is a defining characteristic of exponential random variable. So what exactly does this memoryless property mean? It simply means the future does not depend on the past. The future is independent of past given the present. Okay. So this particular terminology, when I want to translate into a mathematical equation, past and future can be related by conditional probabilities, right. So I will relate it using the conditional probability, probability of x greater than s plus t, given that x is greater than s is equal to probability of x greater than t. Now understand this, x is nothing but a waiting time distribution or a lifetime distribution. So it can be a lifetime of a component or waiting time for a claim, anything. So what does this particular property say? Okay, before doing that, let me enlist all the details of this. Let us say x is the lifetime of the component. Your small s that is given is 1000 hours and small t that is given is 500 hours. Okay. So now we are asking a question, if you consider the left hand side, what is a probability that a component, remember this is a survivor function, what is a probability that this component will survive for 1500 hours given that this component has survived for 1000 hours. Okay. So that is the meaning of this particular statement. So because this thing is, t is 500, this is 1000, so together this is 1500, and you are asking x greater than 1500 given x greater than 1000, right, and you are calculating probability of that. So it is a probability that a component will survive for 1500 hours given that it survived for 1000 hours. What does the answer say? If I have exponential distribution, it is nothing but probability that the component will survive, a fresh component will survive for 500 hours. Okay. So this is the beauty. So it does not depend on the past, the component does not age with time, so it does not have memory. Okay. So again I will reiterate what I have meant. The probability that 1000-hour-old component will survive for another 500 hours is same as a fresh component survives for first 500 hours. That means the component does not age. Okay. Whether this is true in real world or not is not, we will not answer that, but this is how exponential distribution treats our component. Okay. Let us move on, and let us move on to prove this particular property, memoryless property. It is very easy to show using conditional probabilities. So let us try to do it by hand first and then see what is happening. So it is a probability of x greater than s plus t given that x is greater than s. So this, you treat this as event A, you treat this as event B. Okay. Now because this is a conditional probability, it is a probability of A given B. So this is equivalent to saying probability of A intersection B, that I can write as x greater than t plus s comma x greater than s upon probability of x greater than s. Okay. So this comma you can interpret as intersection of two sets, because I have not yet defined the joint distribution. You can interpret this comma as intersection of two sets. Okay. Now you look at this set, if x is greater than s and if x is greater than t plus s. If x is greater than t plus s, then isn't it natural to have x greater than s, right? So this particular set which I have called as A and B, and we are talking about A intersection B, but this A is actually a subset of B. So what will be A intersection B? It will be A, because A is a subset of B, A intersection B will become A. Okay. So, that naturally turns out to be probability of x greater than t plus s upon probability of x greater than s. Okay. If this is true, then do I know what is a survival function, survivor function? This is s of t plus s, which we have defined, and this is capital S of small s, right. I definitely know this, which is e raised to minus lambda times t plus s upon e raised to minus lambda times s, correct. And then if you do some algebra, it is very clear that this thing will get chopped off with this, and what I am left with is e raised to minus lambda t. But we have seen that this to be a survivor function of st, which is probability of x greater than t, and therefore I have proved the memoryless property of a exponential distribution. So, this is basically the printed version. You start with a definition of x greater than s plus t, write it properly. Again, this is a subset of that, and therefore the next line automatically follows, and after following that you can easily substitute. I have substituted that, and this is the memoryless property. In fact, you can do further, you can actually prove the other way around also. If this is the only distribution, that if this identity is satisfied, that is the memoryless property, you can show that this is going to be only exponential distribution, because this sum converting into this kind of thing is satisfied only by exponential distribution, which I will give as an exercise. Okay. So, now that we have understood this interesting property of exponential distribution, let us try to do some typical exam type questions. So, when you are dealing with exponential distribution, the typical exam pattern that you have to look for is problems often include irrelevant age so far information, okay, and you have to intelligently ignore that information. So, let me give you one example. This is an example that lifetime of a component is exponentially distributed with mean 100 hours. Notice this terminology, mean 100 hours, and the component has already been in service for 50 hours. What is a probability that it fails in next 20 hours? So, the moment you see this exponential distribution, you will say that whatever it is in service, this information is going to be irrelevant. Okay. So, that is what the main component is. Another component is the mean is 100 hours. So, what will be the lambda? That is what you have to look at. What will be the parameter of the exponential distribution? Correct. So, these are the two things you should be aware of. So, now you are saying that the distribution is exponential. So, it satisfies memoryless property. So, the 50 hours is nothing but a distraction. Therefore, I want to compute probability that the component will survive, a component will fail in next 20 hours. Okay. So, that is t less than or equal to 20 for a fresh exponential lambda. That is very clear. Second part, identifying lambda. Can you guess what is a lambda? Mean of 100 hours. So, expected value of t is 100. So, your lambda will be 1 by lambda, right? 1 by lambda is 100. So, your lambda will be 1 by 100. Okay. Once you guess that, it just turns out to be a simple algebraic calculation. It is 1 minus e raised to minus lambda 20. Okay. So, that is the answer, and it becomes 18.1%, correct. So, there is no brainer here. you have to read the problem carefully, identify the irrelevant information once it is said to be exponential, and then choose the parameter of the distribution intelligently. This should be your strategy to solve the problem. Right. So, now there will be several hidden patterns of lambda, and finding lambda will be your key skill for solving these problems. Let us look at some of the patterns. So, first case 1, where it will be straight away given that lambda is equal to phi. So, here there is no question, lambda is phi, mean will be 1 by phi for our exponential case. Okay. The next pattern, that is claim size is exponential with mean 500. So, here rate is not given explicitly, mean is given, which is 1 by lambda. Okay. And therefore, you have to find the lambda which will be a reciprocal of the mean, correct. So, this is the second pattern. The third pattern is you may be given tail probability. This is the most hidden pattern, where you are told that probability of x greater than 1000 is 0.5. Now, you have to actually guess the lambda, and therefore, that survivor function, the simple form of that survivor function will be of significant help. You simply put e raised to minus lambda x is equal to that probability. So, that is what we are doing, e raised to minus lambda times 1000 is 0.5. So, naturally take a natural log and you get minus 1000 lambda is ln of 0.5. Okay. Just take that minus sign on the other side and you get ln of 2 by 1000 is equal to lambda, and evaluate the lambda. So, these are the three ways your exponential random variable parameter lambda can be given, and you have to guess that lambda accurately. You have to use memoryless property of exponential random variable, and you can solve all problems that are involving exponential random variables. Okay. So, now that we have handled this interesting distribution, let us summarize what we have done. So, what we have covered today is, when you are considering a time to event or time to failure, you are modeling through a continuous random variable. That is what we have covered. In this particular class or lecture, we have covered exponential lambda, where we have shown you the PDF follows lambda e raised to minus lambda x for x greater than 0. CDF has 1 minus e raised to minus lambda x form for x greater than 0 again. Survivor function has a form of e raised to minus lambda x, and mean and variance of exponential distribution are 1 by lambda and 1 by lambda square explicitly. Okay. One more interesting property of exponential distribution that we studied is memoryless property, which says that it does not matter in the past how long the component had survived, the probability of the component will survive for next t hours or greater than t hours is going to be the same as the fresh component. Okay. So, this is the key concept, and it is called as memoryless property, which is very helpful for solving many problems. However, whatever we studied so far, if you recollect the notion of exponential random variable, and you can see a towering peak at 0 and then the exponential decay, are all continuous distributions in that form? The answer is no. Okay. So, we need some different distributions to understand the behavior of those other continuous distribution. Okay. Another interesting aspect is, if you are counting in the Poisson process or Poisson counts how many events will occur, exponential essentially counts what is a time required for next event to happen or a first event to happen. Now, if you ask a question which is fairly general, that is time until alpha th event or 10th event, how will you answer that, right? So, it is basically the question of a time until next event or next 10 events will happen. I want to answer that question. For that I need a generalization, that is the gamma distribution. So, in the next class we will look at gamma distribution, which will answer all these questions. We will also identify an interesting connection between gamma distribution and exponential distribution and leverage that to solve some problems. See you in the next class. Thank you.